LLMs paired with the Lean proof assistant have led to breakthroughs in competition math and more recently, the verification of frontier math results. Lean is a critical part of this process because it helps validate the candidate proofs the LLM spits out. In this conversation, I asked the creator of Lean about how it works and how it will affect the future of math and software verification.
Could that be the end of handwritten math?
Here's the full episode.
There's this famous Dijkstra quote I want to start the conversation with. It's that program testing can be used to show the presence of bugs, but never to show their absence. And my understanding is that Lean and formalizing proofs can be used to show the absence of bugs. And so, in your words, what is Lean and how do people use it to show bugs can't occur in programs?
Lean is a programming language. You can write code, but you can also write proofs. You can reason about your code. You can write state properties about your code and prove them. Lean gives you machine checkable proofs. You can check your proofs and get absolute assurance they are correct. You have many checkers, independent checkers. But you should view Lean as a platform. You can write code, you can write properties about your codes, and you can prove them.
So could you give a concrete example? Because when I think of a proof, I think of what I learned in math, but then how do you couple that with the software that we write?
Yeah, it's a great question. It's not that different from math proof. Lean is actually very popular for math, but for software verification, right, there are two very different use cases. You can reason about Lean programs. Lean is a programming language. You can write programs in Lean itself. Then a Lean program is not that different from a definition you have in math. The techniques are very similar. But if you want to verify programs written in a different programming language, there are basically two different approaches. One of them, they translate, it's called shallow embedding. They translate for Rust. This happens today. We have a tool called 𝗪𝗍𝗍 that maps Rust into Lean. And you can verify the Lean translation, right? And there's another technique called deep embedding, where you have the semantics. You write a semantics of the programming language of C in Lean. And now you have a data structure that represents a C program. And you can state properties about it. It's almost like your programs become Lean objects, right, that you can reason about.
To make it really concrete, to give someone a sense of, here's this thing I want to prove about a simple C program, maybe like no buffer overrun or something like that. Mm-hmm. What's the step-by-step where we could use Lean to prove that?
Yeah. Let's get array. You're trying to access an array in C. You want to make sure the index is in bounds. You're not accessing elements that your array, for example, has 10 elements. You're not trying to access elements 11, right? Basically, you can write that. You can write in Lean that the value of I at this point in your program is going to be greater than or equal to 0 and less than 10, right? You can write that as a mathematical statement, right? Another way to view is that if you can express in math what you care about your program, you can verify using Lean, right? That's another way to view it.
So I have my C source files, and then somehow there's a equivalent Lean proof that's almost like metadata on top of the C program.
Yes.
Yep. And that's a line-by-line proof, and Lean will go and check.
Exactly. People will build automation for automating the process. They're going to use techniques like hot triples that says, like, we have a precondition, some mathematical facts that should be true before executing that statement, the statement, and what is true after, right? And they will have a lot of automation to process. Makes your proof modular, right? I mean, complexity is a challenge in software verification. Handling the complexity is a big deal, and there will all these frameworks for verifying programs, they are trying to manage the complexity, make your proofs modular. even with AI now, AI can prove things automatically for us, but they have to be modular to the proofs if you want them to scale.
And what you're saying sounds similar to in software, where you have to write it cleanly. It needs to be easy to edit and reason about. So it's almost like a second software layer on top of the software.
Yes, you can view this way. You can also flip and imagine a future where you're writing what you want mathematically, precisely, and AI is synthesizing the codes and a proof that the code that was synthesized meets your specification, right?
Oh, interesting. So you could start by writing what you want to be true,
Yes.
and then
ask the AI, please.
And AI is gonna just go and hammer at it till the lean proof says you're good.
Yes. It feels like science fiction. 6 months ago, I would say this is science fiction. But for example, now a colleague of mine, 𝗵𝗵𝗀𝘀𝗀𝘀, a few months ago, she started a project I thought was 6 months ago, I would say it's not possible at all. She said, we have zlib, this compression library written in C. And she said, she creates a very complicated prompt for AI saying, I want you to translate to lean, ensure the lean version passes the test suite for zlib. Then I want you to prove that if you compress data and you decompress, you get the original data back. It's a really strong property, right? And believe it or not, the AI, after 1 week, succeeded doing the whole thing. And now it's just asking to optimize the code. But you cannot break the proofs. I mean, you have to still prove all the properties you care about. I mean, compressing and decompressing, getting the data back is a really important property for a compression engine, right? Yeah, this is rich now. I mean, it's surreal.
I mean, it's crazy. And I hear in the industry, a lot of people, they use a really comprehensive test suite coupled with AI to do some really amazing rewrites because they have some more confidence that the rewrite is accurate and the AI can check itself. And it sounds like a specification is even better than a comprehensive test suite.
Yes, because your code from Dijkstra captures perfectly, right? So with a test suite, you can show the presence of bugs, but not the absence. It's almost like with a good test suite, you may say, well, probably there are no bugs here, but you may have a really corner case that's not covered by your test suite. But with a proof, you're covering all possible cases. And it connects. So property-based testing is really popular now. People are writing properties they want to ensure they are true, but they are checking with testing, right? But now you can prove them, and you say, look, there's no point testing anymore. I prove it.
It seems like having a well-written specification is a superset of a test suite, but in terms of the human labor required to create a reasonable test suite versus a reasonable specification, how much more work is it to come up with a great specification?
Varies a lot. I mean, the programs, in many cases, it's not uncommon for someone to start developing a piece of software. They don't know exactly what the spec is, right? But you know properties. Usually their properties are very clear in your mind. Another thing that I tell people to keep in mind is that an inefficient program can be viewed as a specification. Usually, writing an efficient program is way easier than writing the super efficient one that has many clever tricks. You can write this is what I want, in a very naive way. And you ask the AI, look, generate the efficient version and optimize and prove that it's equivalent to my inefficient one. There are many scenarios. I mean, I will not say this specifications are always easy to come up with, but properties, usually the developers have good ideas about properties they care about. As inefficient program is a spec, right? So you can view it as a specification. And the technology, formal verification complements testing, right? I think your quote from Dijkstra captures perfectly.
And I think I saw this on Twitter because Jane Street was more heavily investing in formal verification.
Yes.
And I read their post and they talked about this. I think it was a cell for some software that was entirely formally verified.
Yes.
And the main drawback to why it wasn't, how much more time would it take writing a program versus verifying it?
Your example, cell4, is a great example. This was a major milestone. It's a microkernel they verified, done manually. It was before AI. This project was done before AI was a big deal. And it's a lot. The cost is super expensive, right? At AWS, we have been using formal verification for a decade, but only for the super safety critical components because it's expensive until now, right? With AI, it changes the game. You have to come up with a spec, but this is not the most painful part. The most painful part is to develop the proofs manually, if you have to, before AI, and maintain the proofs as you change the codes. Imagine, I've seen people complaining that, I changed the program right now. I have a bunch of failures in my test suite, and I have to patch, go one by one. Imagine with proofs. It's the same process. You have to fix the proofs. Sometimes you don't remember anymore why the proof, what's the story behind this proof. It's a lot, but AI is extremely good at proving, writing formal proofs, maintaining formal proofs. For example, yesterday I was changing something in Lean. I want to modify some proofs for technical reasons. And I didn't even know what the proofs were about. Someone else wrote them. I said, look, I want you to, I asked AI, rewrite these proofs without using this feature because I'm going to change it. I don't want to break the libraries. Instantaneous, it came up with the new proofs for me. It's really good. And this is crucial for making formal verification mainstream because otherwise maintaining the proofs was almost like if your program took X amount of time to do the formal verification in the past, it would take 10x. That would be normal. But imagine if your program is changing. That's something that's really common. Now you have to keep maintaining the proofs too. It's a lot of work. But AI eliminates this pain for us.
You mentioned that Lean is, because I hear it as a proof assistant, but,
Yes.
And then you also said it's a programming language.
Yeah.
Is that typical for proof assistants to be both a programming language and a proof assistant?
Some of them, especially the ones that are based on dependence type theory, they are like Rock and Lean are programming languages and proof assistants, right? You can write definitions when you're defining concepts in math, but some of these definitions can be programs. And you have types, you have structures. It's a programming language, but is in the family of called functional programming language. It's a specific kind of programming language. For people that are familiar with programming languages like Haskell, Lean is close to Haskell. But with the support for proofs. That's a way to view Lean.
Are there major use cases where people use it as a programming language but not as a proof assistant?
Well, the first big use case is Lean is implemented in Lean.
Right.
We have many of our tooling is implemented in Lean, like the documentation authoring system called 𝗪𝗀 is implemented in Lean. The build system that's called Lake is like Lean Make. Lake is implemented in Lean. At AWS, we have a compiler for AI accelerators. It's 500,000 lines of Lean, and it's using Lean as a programming language. They're proving some properties about the program using Lean, but the main goal is to use Lean as a programming language in this project. The proofs are like a bonus, right? That you can get the proofs and find problems in the design.
I think most people are familiar with programming languages and the tool chains they have, but what are all the major components that you would need for a proof assistant?
It is not that different. I mean, if I use to modern programming language like Rust, the tooling, for example, Lake is our cargo, right? I mean, you're going to open Visual Studio Code, same way, and you're going to get all the IntelliSense. One big difference is that we have something called the info view in Lean. Your screen usually is going to be split in two. You have your file on the right-hand side. You have the info view that tells you information about your proofs, about your codes. It's giving you constant feedback about your developments. That's basically the main difference. But the tooling, VS Code, everything works the same way. I mean,
it seems like a programming language is the fundamental layer, and then there's some additional layer on top that keeps track of that stuff.
Good question. In Lean, you have definitions that are your program, but you have theorems, statements. Right? You're going to say, for example, factorial is always greater than or equal to 0 or something like that. Or if you add two even numbers, you get an even number. You can write statements like that. And immediately you can write actually a program that's the proof. But most people don't do that. They go into something called 𝗪𝗪𝗃 mode. You can view as a domain-specific language for writing proofs. In Lean, when you write by, it switches to this domain-specific language. And you have steps like simplify my goal, the state of my proof. You can say, apply this rewriting step. Apply, for example, we know that x plus 0 equals x. You can ask Lean, apply this rewriting. And you're going to see in the info view the state of the proof changing. You get immediate feedback, and you get this feeling that you said you keep applying transformations to your proof step by step. You can see what's happening until you get no goals left. I mean, you are done. The proof is complete. And some people view this process as a game. I have users that told me, you built my favorite computer game.
That's funny. Is Lean itself verified in Lean?
Lean is a massive program. You only have to trust the kernel. The kernel is where the proofs are checked. Lean itself is the kind of program that, because there are so many new things we are adding, it's not even clear what is the specification. For example, what is the specification of a simplifier? You can write general ideas, but users, they want to be able to customize the behavior. They keep asking, they keep changing the specification all the time. I want this, I want that. No, add this knob here. So it's really hard to have a full specification of Lean. But the kernel is possible to have a specification. We have a kernel. The kernel that comes with Lean is not verified. But there are other kernels that you can use. One of them is implemented by Mário Carneiro. It's called Lean for Lean. And it's implemented in Lean, and he's verifying. He's proving that this kernel has been verified with respect to the semantics of Lean. This is a cool project. But for us, having multiple kernels is the best way to ensure that your results are correct. I mean, some users implement their own kernels. We have kernels implemented in Rust, in different programming languages.
And when you say kernel, what's the responsibility, or what's the inputs and outputs of that portion?
Yes. In Lean, proof checking is type checking. These kernels, they are type checking your programs. I mean, basically, you can export your Lean developments. You get a big blob, and you read this blob, and they're going to check if, when you say we have a proof in Lean, basically you have a term that has a type, and you're checking if the type of this term matches the type that you claim it has. For example, the example of the even numbers. This is a type in Lean saying that the sum of two even numbers is an even number. You can view that each is exactly a type in Lean. And the proof, what the kernel is checking is whether the type of the proof matches the type you claim this term has. I mean, and the kernel will check, it will do this type checking. The kernels vary between a high-performance kernel, it's like 5,000 lines of code. I mean, the goal of the kernel should be something you can write yourself. Of course, sometimes people put bells and whistles, like one thing concern people have is like, okay, but how do I know? Suppose that I wrote 𝗪𝗲𝗄𝘀𝗀 last term in Lean. How do you know that when you exported, it's really 𝗪𝗲𝗄𝘀𝗀 last term? It's not 2 + 2 = 4. I mean, and people, some external kernels, they write printers. I mean, it will print the statements that has been proved, all the dependencies. You can have all these fancy tools to make sure you're not being misled.
Lean, obviously, it's so powerful, and I see on social media all these amazing results from formal verification. I want to know, what are the top ones that you think of, or top examples more recently that have impressed you that Lean was able to accomplish?
Well, there are so many, I mean, that I thought it was impossible. For example, getting a gold medal in the International Mathematical Olympiad. A few years ago, everybody thought it was impossible. Now, everybody, they use it as a benchmark of an easy problem. They say, oh, this is like an IMO problem. I mean, this is easy. But it's not. I mean, these are really challenging problems. The other conjectures that people close using Lean, AI with Lean, also impressed me. There's this unit distance conjecture for others. First, OpenAI proved using formal, right? Was not formal. And we have a system now in Lean. It's a website where we call 𝗵𝗵𝗀𝘀𝘀𝘀, where we collect challenges. The same 𝗂𝗵𝗫 saw this proof from OpenAI, and she puts on 𝗵𝗵𝗀𝘀 as a challenge, saying, okay, I want to see someone formalizing. We knew it was huge to formalize. It's serious math, it depends on. And 𝗪𝗫 from OpenAI, he submits a 1 million line proof for formal proof in Lean for this conjecture. We estimate, I mean, the background math that is needed for the proof, we knew it would take months, I mean, for experts to do by hand. I mean,
how long did it take in that case? Like the time from when the proof came out to when the challenge was solved on the Lean?
I think it was 1 month.
Yeah.
And after Kim was I think less than 2 weeks after Kim puts as a challenge on 𝗵𝗵𝗀𝗀, it took, I think, 2 weeks to get or less. I mean,
that's insane.
Yes, yeah.
We talked about verifying programs, but also there's using it just directly for mathematics, like in this case. How popular is Lean in terms of when you look at the users of Lean, what % are using it for software engineering? What % are using it more for just direct math?
Well, historically, Lean got popular first with math, right? I mean, with the beginning of the Lean Mathematical Library in 2017, we had like a big project called Liquids Tensor Experiments. It started beginning of 2020. It was a big deal because it was to verify a result from a Fields medalist, Peter Gscholte. It's a result he was unsure about. He has not published. He felt like this was one of the most important results in his career. He wanted to be sure it was correct. It was done manually, the verification. Was a big deal because the team that formalized, led by 𝗀𝗵𝗀𝘀𝗀𝘀, they not only formalize the results without fully understanding, they do not fully understand the proof. But having this info view helped them, guides them step by step. they formalize and simplify the proof without fully understanding the proof. It's mind-boggling, right? I mean, how can you simplify a proof from one of the greatest living mathematicians without fully understanding it? I mean, but they manage to simplify. It's almost like when people do refactoring coding, you start changing the codes. It's faster now, but the programmer doesn't really know why. I mean, it felt like that. It's like you have a gut feeling. I mean, that you're going the right direction. And this, for us at the time, lots of people got excited about Lean, the math community, because of these projects. It's shown that's not about verifying, but enabling people to work together in large numbers, because you can trust, you don't need to trust someone else's proof, right? They can fill holes for you. This was, I mean, what attracts a lot of attention from the math community. Then came Terence Tao. He started using after this project. He has really cool projects with and without AI. And he got addicted, actually. I think the first time he used it, he said, I don't think I'm going to do it again. The formal proof. 1 week later, he had another project using Lean, and he did a new result he had.
When you say addicted, you mean because that game, that like completion engine?
Yeah, some people, we feel like when I talk to professors that use Lean for teaching, they tell me that the class is more or less split. Some people love it, some people don't like. But people that like problem solving, people that get medals in the IMO, they love Lean because you get this excitement of solving. It's like solving millions of really hard Sudoku problems, right? And you can keep solving one, and it's easy to get. I mean, I'm a Lean developer, not a Lean user, but when you're developing Lean, I'm coding in Lean, and sometimes I have proof things. It's really easy to get addicted and get lost proving things. You get this buzz every time you prove something.
You mentioned the IOI gold medals. How is Lean used in that kind of, I think maybe you're referring to 𝗪𝗵 by DeepMind or maybe something else?
Yes. DeepMind they got in 2024, was a big surprise. In 2024, they got a silver medal. And now we have gold medals from startups like Harmonic. ByteDance got a medal. I never imagined ByteDance, they're behind TikTok, right? I didn't even know they care about formal math, but they have a formal math team. They got medals also. Their prover is really good.
So how does it work? Let's say, I mean, there's a series of math problems. Lean is just used for verification, right? So I imagine there's other components there.
Yeah, there's the AI. You can view it like we have Go that was very popular with AI. The AI is playing the game. I told you that many people see Lean as a game. It's the same. I mean, the AI is viewing Lean as a game. They have the statements of what you want to prove. You have the by keywords. Now you have a blank fill. Make sure that you have no goals left, right? It keeps applying steps in this game and seeing the state of the boards, right? That's the info view changing. And the AI, they use reinforcement learning for trying to get to no goals left. It's a single player game. Some people play together these days, but yeah, the AI is learning to play the game.
So before we were talking about that game, it kind of starts with the specification. So in that case, then the problem is kind of the specification, and then it hammers away.
The problem, you have basically for each problem in the International Mathematical Olympiad, someone translates to Lean the statements. It's super important to have the mathematical library because you want to be able to talk about the problems, right? For example, suppose the problems uses the real numbers. You need a definition in Lean, and we have it inside of MathLib, the Lean mathematical library. So the first thing you have to be able to write the problems in Lean, and this now because of MathLib, it's easy part. And after that, you have to provide the proofs. I mean, sometimes some problems you have to come up with a definition to, some objects you have to create that has some property. But yeah, that's how it is. I mean,
I remember you said one of the first use cases of Lean was this Fields medalist had this novel mathematics, and then we used Lean to verify it. But can Lean be used with LLMs to generate novel mathematics or just verify existing?
It's a good question. I mean, we don't see lots of evidence. We see now evidence it can find novel proofs, right? But coming up with new mathematical concepts is still at the limits, right? I mean, right now, in this Lean-eval, we have challenges where the AI has to come up with the objects themselves, right? I mean, but people will keep investing in this area. I would not bet against AI here. I mean, but right now we don't have evidence they can come up with new math.
OpenAI, Anthropic, Cursor, and Vercel all use this product to make their lives better. And the problem it solves is when you're building SaaS or an AI product and you want to sell to other companies, there's all these requirements you need to meet. There's SSO, there's SCIM, there's RBAC, there's audit logs. These are all things that take time to integrate, but aren't the main focus of your app. WorkOS is an API layer that lets you meet all of these requirements in just a few lines of code. So let's say you have a new SaaS product and you want to sell to other companies. WorkOS will solve all of these critical feature gaps for you. You can check them out at workos.com to learn more and get started. And I appreciate them for supporting my work and sponsoring this podcast.
When I see on Twitter this, major conjecture, they made headway on it. It's that they made headway on confirming something.
Or disproving. They also have these 1 million lines, they shown the conjecture was false. They have a proof showing that it's false. But it's a formal proof. They did not came up with a new theory or anything like that. They are coming up with a proof, right? I mean,
at what points would you say someone should evaluate formalizing something in Lean?
I think if it's safety critical or if you don't understand really well, I mean, this is important part. I don't really understand. Anybody that went through the process of formalizing something understands the subject way better after that. I almost feel like, I remember when I was in college, people would say, wow, after I implemented this algorithm, now I understand it's much better. The next level is that you implement the algorithm, you prove the properties you expect, your level of understanding grows, right? I mean, another cool thing is that it enables you to be much more bold on your optimizations. Because sometimes, I've seen that all the time, people fear implementing optimization because they don't really understand why the piece of software works. They feel like if I do that, it still works and it's faster, but they are not confident. With proofs, you eliminate this discomfort, right? You can prove it again, or the AI can prove for you, or find a counterexample. They are good at both things.
But if you were to speculate or draw out into the future, maybe 3 to 5 years from now, if the cost of formalizing things goes down, how does that change software? How does that change, handwritten math?
Oh, I think it will change dramatically, right? We have to keep in mind the big labs, they only start training for formal verification Lean very recently, right? Seriously. Before that was like, oh, it's in the data sets. I mean, you don't really have the reinforcement learning pipelines to optimize. The behavior we see today that is already amazing will get way better in the future. The costs will reduce. Programming languages like Lean and Rock will become more mainstream because of that. Many people are not so... In the past, people would say, oh, functional programming, I don't like it. But if I'm not the one that's writing most of the code anyway, it doesn't really matter. What matters are the specification level, right? It doesn't really matter how the code has been written. yeah, I think it will change a lot because of that. At least that's the direction we are pushing into.
What about, let's say, 10 years from now, everything's going really well with Lean. Could that be the end of handwritten math or handwritten proofs?
I think there will be always an aspect that is handwritten. Some people like to make a proof look. They want to use the proof as an artifact. You communicate ideas to others. I can't imagine there will always be people polishing, making them super easy to understand for another human to communicate ideas to other people. There will always be people like that. The same way today we have people that we have machines that build furniture, but people, they like to create them by hands and polish them, make them perfect. This will always exist, but it will be a mixture. I will be surprised as if there is someone that's completely AI is not in their workflow somehow, right? I mean, you'll be hybrids, many hybrids. Some people don't feel uncomfortable about this future. But for me, it's super exciting because I view developing software as a super painful process. And with AI, it's crazy how it brings you awareness of how many steps are just repetitive and there's no creativity. You're just patching things, and AI removes lots of this pain, right? I mean, I cannot go back to without AI. I'm looking forward to this future you describe.
Yeah. I guess the thing that gives people, I'm guessing, the discomfort is the worry that if it kept going, then, we need less mathematicians or less computer scientists or something like that.
People don't see that AI can bring more people. There's also the specification. I mean, I've seen people saying, "Oh, we are going to leave AI. We'll come up with new math." But if there's no connection to our world, this is some alien thing that's going by itself. You need an interface. For example, we want to build programs because we want to accomplish something. This something, whatever it is, has a specification. There will be always humans in the loop saying, this is what we need, this is what we want, right? Writing this interface, interacting with the AI. The AI will have math libraries and everything to prove things about these programs we are writing, these artifacts, these whatever we are trying to build. But we have to be able to interact these libraries. We have to understand the abstractions that are there. I don't see humans being eliminated. We are always going to be there. We're in the interface, right? We are telling them what we want, right? I mean, specifications will be there. I can see people always writing codes. Even another thing, a lot of people like to write. They say, I love coding. My interpretation is they love to write prototypes. This is fun. This is the fun part, to try a new idea. But to transform it into a product is never fun. I can tell you, it's never fun. And AI can take over these parts. I mean, nobody really likes doing.
Outside of Lean, I know you worked on the Z3 SMT solver. Yes. And that sounds like a really difficult thing to build. So first, what is that solver in your words? And how does it differ from a SAT solver?
Yeah, I started Z3 long. It's going to be, 20 years ago I started Z3. I mean, when I joined Microsoft Research. Z3 is a SMT solver. It's like a SAT solver, but you have backgrounds, theories, like you have support for arithmetic, for arrays. These are not random choices, right? This is because we use for doing test case generation in software, for doing software verification. Z3 is fully automated. It's a push button. Although Lean Z3 are called theorem provers, they are completely different beasts. Z3 is fully automatic. Lean is interactive. It has automation, but it's interactive. Z3 is not a programming language. It's like you can do. It's more like a constraint solver. It turns out you can prove simple things about it. You cannot do advanced math with abstract math. You can solve constraints with Z3.
What's an example of the inputs to this SMT solver and what you get out from it?
Oh, I can give you one. I mean, that's even in the Z3 manual. You can encode a Sudoku problem as a set of constraints, and you can ask Z3 to solve, and it will give you back the answer instantaneously. For real applications, Z3 was used very successfully for finding bugs in software. People would convert, for example, suppose that you have a path in your code, you know that has a security vulnerability, but you don't know which inputs to the program allow you to execute this path. You can convert that into a set of constraints that you send to Z3, and it will say unsatisfiable. It means it's impossible to execute this path and you are happy. Or it gives you back an example saying, look, with these inputs, you're going to be able to do it. I mean, and people use Z3 for doing software verification. But because the problem becomes undecidable, at that level, you have many universal quantifiers for stating properties about your program, your pre and post conditions. The solver has heuristics. And this was all before AI. The heuristics were hand-coded, and they will always fail. And for simple things, people would be very happy with the fact that Z3 is push button. But when the property is not trivial, they would come back saying, come on, I know the proof. I mean, why Z3 can't find it? That's why Lean started. I started Lean to make sure that we would have a system that's really good for software verification, right? Z3 was successful for finding bugs, but not so much for software, for proving the absence of bugs. It was never super successful there. But Lean was born to fill this gap.
You said undecidable, but in practice, in the real world, if you run it, does it typically terminate?
Yeah, great question. Z3 goes the whole complexity ladder, right? So you have sets, you have NP complete, P space complete, XP complete. You have the whole until undecidable, right? I mean, surprisingly, even for sets, you can write really tiny set problems that are really hard to solve. No set solver will solve them. But in practice, the problems we get from hardware verification, especially if you bound everything, you say, oh, I'm trying to look for a bug in the first 10 steps, right? Everything's bounded. You're not trying to prove, but you're trying to capture a class, like a space of scenarios, right? They are very effective there. I mean, I think the lesson there is that programs and hardware, they're not correct by esoteric reasons, right? They are correct because for very simple reasons. I mean, that's why these tools are super effective there. Yeah, but when you get to undecidable and you're trying to prove, even if the property is not trivial there, I mean, it runs out of steam. I mean, and they time out frequently. And sometimes there is a colleague of mine here at Amazon in Minator, like, chooses the name proof instability. Because sometimes if you change the problem, you just flip. I mean, you have A and B, you write B and A, where B and A are complicated formulas. You may fail to prove. And when she was just trying to maintain things, proofs would break if using this kind of technology. But with Lean, she switches to Lean and it's super smooth, right? Because you're controlling the proof.
In the Lean case, why is it so much more efficient?
your proof is basically, you can view is the sequence of steps for solving the problem. In Z3, you can view that you have only one proof step, solve, right? I mean, you're saying you have options to solve, flags, but you have you cannot influence what Z3 is going to do. It's much harder to influence this kind of system. In Lean, you can, if you want to give a super detailed step-by-step proof, you can. You can use proof automation like is available in Z3, but you can also break it down step by step. And the fact you can do that, humans can do it, but the happy surprise is that AI can do it, because now you can say step by step why something is true. The AI can convince Lean that it can provide a proof. I mean,
when you were working on Z3 and Lean, what was the most technically challenging part that you had to build for either project?
I underestimated how much harder Lean is in comparison with Z3. It's orders of magnitude harder. I mean, I talked to many colleagues about that, why I felt like Lean was so much harder. I think it's the surface, the interface with humans is way... For Z3, you have a defined language it's called SMT-lib. It's very simple language. It's not meant for humans, it's meant for tools. I mean, Z3 is used as the back ends of many different tools. Some program is generating input for Z3. And people expect a counterexample or saying it's impossible, it's unsatisfiable to come up with a counterexample. The interface is really, really simple, right? You can view Z3 as a command line tool that you pass this file on this very low level language that's super easy to parse, and you come back with yes or no. And Lean is a programming language, you have libraries, you have mechanisms, you have interactivity, you have user interface, you have LSP, you have build system, you have this, you have that. It is so vast. I mean, that's another challenging part for me. As I mentioned, Z3 was a back end. The Z3 users are very sophisticated software developers, people that speak the same language I speak. It's way easier to talk to people that speak the same language. With Lean, it's completely different, right? The first users are all math people. They have a completely different background, different expectations, different everything, and a different community. And then you have people that want to use Lean as a programming language. You have... I'm not a programming language person. My background is automated reasoning. And yeah, it's different language, different expectations.
Was there like a singular component that was just really technically challenging?
I told you that Lean is implemented in Lean. Well, of course, it was not always like that, right? I mean, it had to be implemented in something else at the beginning. The switch from originally was 𝗧𝗵𝗵𝗀. The switch from 𝗧𝗵𝗵𝗀 to Lean was extremely painful. Really, really. I remember I literally want to cry when I managed to compile Lean with Lean. I was just 𝗬𝗵𝗫 and I at the time were building Lean 4 together. But this was before we had a non-profit for Lean. I remember calling him and I said, wow, man, it's insane. I mean, say, are you not excited? He said, yes, I am. I mean, I'm super excited.
What made that switch hard?
The first thing is imagine you're going to implement the language in itself. The first thing you want is to minimize the number of features as much as possible. So you want to implement Lean using bare bones features because you're going to have to be able to compile it with itself. Then, now you have like 100,000 lines, more or less. I don't know the exact number, but it was between 100, around 100,000 lines. And you start trying, compile, you fail the first file. You cannot even compile the first file in the pipeline, that more than 1,000, and the first one fails. Then you fix the bug, you can compile the first one. Then you can compile the second, and you keep moving, and you're always finding discrepancies between the new and the old one. And you're trying to reconcile, make things easier for the new one. Because you want to replace the old one. And this process is painful. And Lean is a complicated language because of these dependence types and so on, the proofs. For example, when you're implementing Lean, you still need some proofs there. There are some basic proofs you need, but you have to construct these proofs without no interactivity, nothing, bare bones. You have to provide the proof term. It's almost like programming in assembly the proof. This was also super painful.
Oh my God.
Yeah, but it took. Yeah, many people thought we were going to fail. Sebastian and I would not be able to do it.
100,000 lines is a lot, like all human written.
Yes,
too.
all human written, yeah.
We talked a lot about Lean, and I know there's competitors to Lean. What are the pros and cons of the different proof assistants? In what scenarios is one preferred over the others, for instance?
The first disclaimer, I have a completely biased person here, right? But I can tell you what users tell me about. For example, one thing the users love is the fact that Lean is super extensible. Because Lean is implemented in Lean. You can add extensions to... Imagine you're doing your math proof. In the middle of this math proof, you say, oh, I want this fancy automation here. You can write in the same file. Or the AI can write for you the extension for automating a proof. And it will do it. Even the AIs, they know about the fact that Lean is extensible. If I ask the AI to isolate an issue in Lean, I give the AI a Lean file, it will start writing a Lean metaprogram, a program about the Lean internals to validate the conjecture it has about why it doesn't work. It's crazy. The AI keeps writing Lean meta extension there. The fact that Lean is extension is really popular with so many people. For example, there is 𝗵𝗺, he's a French mathematician. He wrote something called Lean verbose. Lean verbose he uses for teaching. We have this language for writing the proofs, but he made the language look like English. And he has the info view now is a point and click. You can click there. It gives you suggestions about the next move that's written in structured English like you find in a textbook. You see, the student has a really good idea on how to write an informal math proof. And he did that without asking me any questions. All this stuff, the point and click, the new language, the new interactivity, he did all by himself. He's not a computer scientist. He has a math degree, and he did all this stuff. And it's for English and French. You can choose. You can write the proofs in French. It looks textbook proof. There are people that write visualizations, right? You want to you're trying to prove something about a math object. You can write an extension that visualizes these objects in your info view, right? There are people that write new domain-specific languages embedded in Lean for different purposes. For example, for protocol verification, there is a language called 𝗲𝗀. It's a Lean file. You open 𝗲𝗀, you feel like it's a different system for protocol verification, but it's just a Lean file with these extensions for protocol verification, the language for writing protocols in a very convenient way. These folks wrote the whole thing without ever talking to us. They only talked to us after they had done it. Said, look, I want these parts of Lean to be faster. That was the only interaction we had. And so interactivity is a big deal. Another big deal now is the mathematical library. It's vast. I mean, for stating problems, open conjectures, you need a library with the concept to even state the problem, right? So Lean has a massive library and a massive community. The community also plays a big role. People, before AI, I think now most people ask questions about Lean to AI, but in the past, people would go to the Lean Zulip channel, ask a question about Lean, they would get an answer in 5 minutes. I mean, people would say it's human-based AI. I mean, people would be writing answers instantaneously to your problems. The community played a big role. Another one was we listen to our users. I mean, the math, I mean, if you talk, for example, 𝗪𝗵𝗵𝗀𝗀 was the first user. I mean, he has math backgrounds. You ask him, look, he said, look, I could ask anything, any new feature, I would get back the same day. I mean, the fix, the new feature, same day. And this attracts people, right? I mean, because you're making improvements, making sure the system does what they want, they come back for more. I mean, this also has a huge impact in growing the community.
When I was doing some research, there was this idea, I think you mentioned in this conversation too, there's this dependent type proof assistance, and then there's higher order logic. What is that difference there?
At the beginning, when I started Lean, I won't choose higher order logic because it's much easier to implement. I mean, dependent types is way harder. But the math community, I mean, Jeremy is the one that convinced me that I would never be able to attract serious mathematicians, like Fields Medal level math people with higher order logic, right? His point is like higher order logic is good for concrete math, but if you want to talk about abstract objects, dependent type theory is way more powerful. And it's beautiful. It's easy to explain why it's called dependence. For example, you can have a structure in Lean when you have several fields like X and Y are natural numbers or integers. Let's say they're integers. You can have another field. The type of the field is a proof that X greater than Y. The type of this field is X, let's call greater. Colon, you say X greater than Y. The type depends on the value of the previous fields. That's why it's called dependence type theory. You can have types that depends on the values of other parameters, other fields, and so on. But the beautiful thing about that's in this, you have this very small language that is so expressive. For example, this field now that's a proof, you have to provide a proof. You can view it as invariance. I can only build elements of this type if I give the X and Y, like in other programming languages, but I have to give a proof that the X is greater than Y. It's impossible to construct elements without providing this evidence, right? You can view this as invariance. You don't have to invent invariants, right? The language is just the fact you have these dependencies you can express. In the functions, you can have a function, for example, that says takes a X, a Y, and a proof that Y is different from 0, right? I mean, it's impossible to call the function if you do not provide evidence that Y is different from 0. This was always cool. But in the past, people would say, wow, providing these proofs is really annoying. But with AI now, the AI can synthesize the proofs for you. And it's really cool.
In higher order logic, though, could you express the same?
No, you don't have you lose the dependencies. For example, one thing that you cannot do in higher order logic, in Lean, in serious math, people, you have a bunch of structures they manipulate. You have like something, a field, I mean, a ring, a group. You can write a function in Lean that takes a group and returns a new group, a new structure. you're not you don't really care about the elements of the structure. You are viewing the structure as a first-class citizen. That's something that the dependent type theory can do easily, and in higher order logic you have to play in coding tricks. It is a mess. I mean, some people say, "Oh, it works for math." None of the mathematicians agree with these statements. None. I mean, you talk to 𝗪𝗪, to 𝗪𝗪𝗀𝗀𝗀𝘀, 𝗂𝗵𝗵𝗀𝗀𝗀, 𝗂𝗵𝗵𝗀𝗀𝗀𝗀, 𝗂𝗪𝗪, they would say, no, you have to do dependence type theory. I mean, that's another example for me that listening to your users is important. If you want to appeal to this community, it's totally okay to say, I don't care about this community, but if you care, listening to what they really want is important.
So when we think about the future of Lean, I'm curious to hear your thoughts on where you think Lean is going, things you're excited about in the future. You know, what might it look like in a few years?
Yeah, one thing, we have these non-profits behind Lean since 2023. I mean, Lean is 13 years old. The first 10 years was a research project, right? I mean, only when we got the non-profits behind Lean that it became, you can view as a product. You have a team of engineers. And we managed to do it because the impact on math, right? But 𝗪𝗪𝗀𝗀𝗀𝗀 and I mean, we co-founded these nonprofits. What we are really excited about is Lean as a programming language. A programming language is where you can prove things about your programs, right? And that's a direction we are pushing really hard, right? Lean to. We are super grateful for AWS, Amazon. They're making the largest donation so far to these nonprofits, where the goal is to accelerate this path. I mean, Lean is doing super well in the math path, but let's make Lean as a programming language, Lean as a system for software verification, hardware verification. Let's push to the extreme. Let's give some love to these people, to this path that's right now, we do not really have funding to push seriously this path. That's the non-profits, right? For me, to be in a world where you can reason about your codes is part of my life. I'm not writing unit tests anymore. I'm writing properties and proving them. The AI is proving most of them for me. This is a direction we are pushing hard. And one thing that people don't realize is that when you have proofs, it enables optimizations for free. You can ask for example, today, if you ask the AI to optimize, you have to inspect the code to make sure no bugs were introduced in the process. But if the AI is telling you, look, I optimize it still computes the same thing, here's the proof. This is a game changer in my point of view.
Yeah, I've heard multiple people say this decade will be the decade of formal verification of software, and yeah, maybe Lean will be a huge part of that.
Yeah, we for sure, we are super excited to make it happen. I mean, we are scalability is super important, right? Because there is a big difference between math and software verification. In math, the statements are usually really tiny or small. I mean, Fermat's last theorem is an example. I mean, it's super small, but the proof is insanely cheap. For software verification, it's the opposite, right? The statements are big, I mean, but the proofs are shallow. The reason why this is true is shallow, but you have to manipulate these big objects, right?
So for someone who wants to learn more about formal verification or learn more about Lean, do you have a top technical book recommendation?
In the Lean website, I mean, we have several books there that introduce Lean, functional programming Lean, theorem proving Lean, mathematics in Lean. The mechanics of proof is great for educational purposes. We have a collection of books. If people go to lean-lang.org, you'll find all these books there. But one thing I tell people these days is that learning Lean using AI is super efficient. I mean, you keep talking to AI in natural language, asking what do you want, asking it to write examples. Many people split the screen in three now, right? We had the Lean codes, the info view, and on the bottom now, many people now using an AI agent there that's writing the codes and explaining in natural language what's going on there. It's a super effective way. I mean, 𝗪𝗪, he told me when he learned Lean, he uses an old version of it. Was before agents. He would have the 𝗪𝗵𝗄 on one window and the Visual Studio Code in the other window, and he would copy and paste between them. And that's how he learned. But now it's even more effective with the AI agents. It's easy to pick up. I mean, if you just talk to the agent. Sometimes people say, how do I start? Start talking to the agent. He will help you. He will customize, right? You can explain what you know already, right? I mean, what's your background? I mean, for example, if you tell, oh, I know Haskell, it's so much easier, right? You can customize the process.
And then last question for you is, if you could go back to the beginning of, building C3, building Lean, and give yourself some advice, knowing what you know now, what would you say?
I'll keep it a secret. I mean, I think ignorance is a bliss. I mean, you don't know how hard things are when you start the adventure. Maybe I'll keep secrets. What I would tell, I think one thing, especially before starting Lean, I'm super introverted. And I would tell, look, you should work on your people skills. I mean, because it helps a lot. I mean, when you have to interact with a community, with people, for me, it was hard to learn that. I mean, and I would tell myself, look, it's really important to have people skills too.
Well, thank you for your time today. I
Thank
really
you.
Appreciate it, Leo.
Thank you.
Yeah.
Hey, thank you for watching this podcast. If you liked it and you want to see the show grow, please support with a comment or a like. Also, if you have any recommendations for people you want me to bring on, please drop a comment. Guests like 𝗪𝗵 Liskov, Mike Stonebreaker, Mark Brooker, these were all people that I brought on because someone left a comment. On another note, aside from the podcast, I'm working on building the ergonomic keyboard that I wish existed. Here's a glance at the prototype. It's a split keyboard, so there's two sides. This is in the case. But yeah, we launched on Kickstarter and we hit our goal within 8 hours of launching. I really appreciate it if you were one of the people who grabbed one of the early units. We're now working on the long journey of building the tooling now. And so if you still want to pick one up, I've left the late pledges open on Kickstarter, so you can grab one there. I'll put a link in the description. Thank you again for watching the podcast, and I'll see you in the next episode.